Hello everyone, welcome to the next session of algorithmic problem solving. In this session, we look at the activity selection problem.
Activity selection problem. The input to the problem is a set of activities with start times and finish times. The output is maximum-sized set of non-conflicting activities that may be scheduled. Motivation. As an example, consider the problem of scheduling classes in a classroom. Here we are assuming a single resource, classroom. Our goal is to maximize the number of classes that can be scheduled in the room on a given day. Interval scheduling. Activity selection is also known as interval scheduling since this is equivalent to the problem of finding the maximum number of non-overlapping intervals that can be selected from a given set of intervals. Maximal independent set. The activity selection problem is also equivalent to finding the maximal independent set in an interval graph. An interval graph is defined with vertices representing intervals. An edge between a pair of vertices represents the intersection of the corresponding intervals. In a graph, an independent set is a set of vertices such that no two vertices in the set are connected by an edge. Finding the maximum-sized independent set in an interval graph has applications in VLSI routing. An example with 4 intervals is shown here. The corresponding interval graph is also shown. The maximal independent set consists of the two vertices colored yellow and red. We will follow a simple template for greedy algorithms for activity selection. We select an unscheduled interval I according to heuristic H. Then remove all unscheduled intervals that overlap with I. We repeat the above process until there are no more intervals to schedule. We will apply various heuristics to the example shown here. For this example, an optimal schedule consists of the two jobs colored yellow and red. Consider the earliest finish time first heuristic. From among the unscheduled intervals, we select the interval S with the minimum finish time. Then, we remove intervals that overlap with S. It can be proved that this heuristic always gives us the optimal solution. In the example shown, the yellow job finishes first and is selected. Since the blue and the green jobs intersect the yellow, they are removed from consideration. The red job, being not in conflict with the yellow one, is now selected. The red and yellow jobs give us a solution of size 2, which is optimal for the example. Now we apply the latest start time first heuristic. From among the unscheduled intervals, we select the interval S with the latest start time. We remove intervals that overlap with S. This is symmetrical to the earliest finish time first heuristic and also gives us the optimal solution. In our example, the red job has the latest start time and is selected. The blue and the green jobs intersect the red job and are removed from consideration. Next, the yellow job is selected, giving us a solution of size 2. Next we look at the shortest interval first heuristic. From among the unscheduled intervals, we select the interval S with the minimum duration. Then we remove intervals that overlap with S. This does not always yield the optimal solution. In our example, the green job is the shortest and selected. Since this overlaps with all the other jobs, nothing else can be selected. So the solution is of size 1, which is not optimal. Next, we consider the earliest start time first heuristic. From among the unscheduled intervals, we select the interval S with the minimum start time. Then we remove all intervals intersecting with S and repeat. This does not always yield the optimal solution. In our example, the heuristic selects the blue job. Since it intersects with all the other jobs, nothing else can be selected. Thus the solution is of size 1, which is not optimal. Finally, we consider the latest finish time first heuristic. In every iteration, from among the unscheduled intervals, we select the interval S with the maximum finish time. Then we remove intervals intersecting with S from consideration. This does not always yield the optimal solution. In our example, the blue job has the latest finish time and is selected. But since it intersects the other jobs, nothing else can be selected. Thus the solution is of size 1, which is not.
We consider the implementation of the optimal earliest finish time first heuristic. Intervals are processed in order of increasing or non-decreasing finish times. Intervals with start times less than the latest processed finish times are ignored. Pseudocode in Python code snippet for the left to right sweep algorithm are shown here. We first arrange the indices 0 through n-1 in increasing or non-decreasing order of finish times. We check if the next start time being processed is greater than or equal to the latest processed finish time. If so, the interval corresponding to the start time is a candidate interval for being scheduled. Else, the same interval should be ignored and removed from further consideration. Next, we consider the implementation of the optimal latest start time first heuristic. Intervals are processed in order of decreasing or non-increasing start times. Intervals with finish times greater than the latest process start times are ignored. Pseudocode in Python code snippet for the right to left sweep algorithm are shown here. We first arrange the indices 0 through n-1 in decreasing or non-increasing order of start times. We check if the next finish time being processed is less than or equal to the process start time. If so, the interval corresponding to the finish time is a candidate interval for being scheduled. Else the same interval should be ignored and removed from further consideration. Here we summarize the greedy algorithms we discussed. Among the 5 algorithms we discussed, only the earliest finish time first and the latest start time first strategies yield optimal solutions. We also discussed order and log n sweep algorithms for both. Thank you. This course is brought to you by Elahay Technologies.